Morning students, myself Dr. S. Vidyanandani, Assistant Professor, Department of Mathematics, SRM District Kottangulathur. Today I am going to take unit number 5 which comes under Advanced Calculus and Complex Analysis. Unit 5, Complex Integration. Unit 5, Complex Integration. Okay, as usual, basic definition quickly I'll recall and then I'll go for the evaluation process. When we say, what do you mean by this complex integration? What do you mean by this complex integration? Whenever we integrate a complex function f of z, we used to call that function as, that integration process is complex integration. So I told you in the previous chapter about z, f of z, the mapping between z plane to w plane. Remember, always whenever we come to this integration, z plane is here, w plane is here, mapping is here. Okay, you remember this idea, this information. What is simple curve? Number one definition, what is simple curve? So simple curve means it is a continuous curve which does not have a point of self-intersection, which does not have a point of self-intersection. We used to call this as simple integration. Self-intersection means it will cut itself. Okay, so this is not simple. So this is simple curve. Continuous, it should be continuous, which does not have a point of self-intersection, is called a simple curve. Right. Next, contour integral. So what do you mean by contour integral? So contour integral means an integral along a simple closed curve. An integral along a simple closed curve f of z dz. So this is closed, right? So we used to call this type of integral as contour integral. Next one is Cauchy integral formula. Very basic one. Cauchy integral formula. Then I'll make you to understand the problem. Cauchy integral formula. So if f of z is analytic, I told you the definition for analytic. It should have a derivative at z0, not only at the point z0, also in the neighborhood of z0. Right. So f of z is analytic and f of z is continuous. And if A is any point inside C, and if A is any point inside this C, and A is any point inside the C, then here comes the definition. Then if n of A, generally I'm giving fn of A will be equal to n factorial by 2 pi I integral over C closed curve. This is the symbol for closed. F of z divided by z minus a whole power n plus 1 into dz. Right? Okay. Now I'll go to the problem. Problem 1. I'll make you to understand this problem. Evaluate cos pi z square divided by z minus 1, z minus 2 into dz, where C is the circle mod z equal to 3. Where C is the circle mod z equal to 3. Right. So remember, this is the given domain. Mod z equal to 0, 1, 2, 3. So this is the given domain. So remember whether the limits, this is nothing but your points which lies inside or outside. So these are all the points which lies, this is your analytic function. Analytic function is cos pi z square. Check whether the given point, at which point we are finding this function is analytic, at z equal to 1 and z equal to this one is analytic. This function f of z is analytic. Check whether this both points lies inside the circle or outside the circle. Of course, this 1, 2 lies inside the circle. Then I can proceed. Now, so 1, 2 lie inside the circle. Inside the circle, mod z equal to 3. So now I'll using partial fraction, we'll split this function like 1 divided by z minus 1 into z minus 1 can be breaked into minus 1 by z minus 1 plus 1 by z minus 2. Now I'm going to multiply cos pi z square out and I'm going to integrate as per the given problem what they ask us. So cos pi z square divided by z minus 1 into z minus 2 dz equal to minus integral over closed circle cos pi z square divided by z minus 1 plus into dz plus integral over cos pi z square divided by z minus 2 into dz. Okay, as per your Cauchy integral formula, this function cos pi z square is analytic and continuous. Yeah, it satisfies the cos pi z square is continuous and this is just analytic. Then it should satisfy this Cauchy integral formula. So then I can use my 2 pi I formula now. So 2 pi I into this f of z. So which is equal to minus 2 pi I into f of what is the point here in which your function is analytic? Which point it is analytic? And the singular point 1. So f of 1, right? Plus 2 pi I into f of 2. You know cos pi z square is your f of z. I mean, I'll circle now. Cos pi z square is what is it? F of z. So what is f of 1? Cos pi. Cos pi is minus 1. So cos pi minus 1 means I'll get 2 pi I plus what is f of 2? Function f of 2, if you supply here, I'll get cos 4 times of pi. Cos 4 times of pi is going to be 1. So I'll get 1 into 2 pi I, 2 pi I. So finally the required is 4 pi I. So finally the required area for this analytic function cos pi z square is 4 pi I. Okay, next problem I'm going to start. Next problem is, okay, I'll go to the next problem. Next problem is this. I'll make you to understand that series, Taylor's and Lorentz, and then I'll teach one by one. So Taylor series. Taylor series. So Taylor series, generally I can expand f of z as f of a plus z minus a f dashed of a by factorial 1 plus z minus a whole square f double dashed of a by factorial 2, etc. So what is the use of this Taylor series and Lorentz series? It is used to expand the analytic function. It is used to expand the analytic function in powers of z. In powers of whom? Z. So which is very important. So Taylor's and Lorentz plays an important role in expanding the analytic function in terms of powers of z. Now problem 1, I mean under this Taylor series I'll give one problem. Expand sine z divided by z minus pi about z equal to pi. Okay, I'm going to transfer something because directly I can't do the problem. So sine z. So I'm going to take z minus pi as t. So z minus pi as t means what will be the value of z? Pi plus t. Okay, which is equal to divided by z minus pi is t. Sine of 180 plus theta is sine t. Sorry, minus sine t divided by t. Now I'm going to expand the series like minus 1 by 2. I'm going to take it out. Sine t, expansion of sine t. Everyone knows the series of sine t. So t minus t cube by 3 factorial plus t power 5 by 5 factorial, etc. It goes on. Now I'm going to multiply minus 1 by 2, I mean 1 by t into this function. I'll get like minus 1 plus t squared by 3 factorial minus t power 4 by 5 factorial and etc. It goes on, right? Now with this information, Lorentz series. So next one is find the Lorentz series. Find the Lorentz series expansion of it should have Lorentz series should consist both positive terms and positive series and negative terms. Okay, positive and negative terms, so it should contain of f of z. Lorentz series expansion of f of z which is equal to 1 by z minus 1 z minus 2 about z equal to 0, valid in mod z less than 1. Second one is 1 less than mod z less than 2. Third one is mod z greater than 2. One by one we'll check it out. Before that, I'll let us split the function f of z as using partial fraction. If you split up, you will get minus 1 by z minus 1 plus 1 by z minus 2. I'll start with the first thing. So mod z less than 1, which means mod z less than 1 means which implies mod z by 2 is also less than 1, right? So whenever this function is less than 1, I can expand using binomial expansion. You all remember? 1 minus x the whole inverse is equal to 1 plus x squared, etc. whenever mod x is less than 1. So the same formula I'm going to supply here, like mod z by 2 is also less than 1. Okay, so what I'm going to get here, I'm going to expand, since mod z itself is less than 1, I can bring the denominator to the numerator, z minus 1 the whole inverse, plus, so here what to take it out, since mod z by 2 is less than 1, right? So I'm going to take minus 2 out, so I'll get 1 minus z by 2, 1 minus z by 2, so it is equal to minus, so z plus, oh, okay, I have to take minus out, only then I'll get 1 by z, isn't it? Yeah, if I take minus out, it will become plus. So 1 minus z whole inverse minus 1 by 2, 1 minus z by 2 the whole inverse. Can you understand? I took minus 1 out because as per this binomial expansion, it should be like that. Okay, so I took minus out, it become 1. So which is equal to 1 plus z square plus x over here minus 1 by 2 here, 1 plus z by 2 plus z by 2 the whole square, etc. It goes on. Okay, so generally I can write this as 1 plus z square. If you want, this one can be written as minus 1 by 2 summation n equal to 0 to infinity z by 2 the whole power n. Okay, this condition is over. I'll make you to the second. I'll make you to the second condition. What is the second condition? 1 less than mod z less than 2, which implies 1 by mod z is less than 1 and mod z by 2 is less than 1. This is the condition I can bring from the given annular region. This is nothing but annular region. Okay, with this information, what is our f of z? F of z already we split it out, minus 1 by z minus 1 plus 1 by z minus 2, isn't it? Now, so I'm going to take the terms out, right? So here 1 by z is less than 1 and z by 2 is less than 1. Okay, so minus 1 by, if I take z out, yeah, I'll get 1 minus 1 by z, right? Plus 1 by, here I need mod z by 2 less than 1. So what to take it out in order to get mod z by 2? Right, I have to take it minus 2 out. So 1 minus z by 2, right? So which is equal to minus 1 by z, bring the denominator to the numerator, 1 by z the whole inverse minus half 1 minus z by 2 the whole inverse. So I can bring you this, yeah, so it is equal to minus 1 by 2, 1 plus 1 by z, 1 plus x plus 1 by z the whole square plus 1 by z the whole cube, etc. Right? Next, minus, this is 1 by z. Yeah, this one is minus half. This one is 1 by z. This one is minus half. So what I shall get here? 1 plus z by 2 plus z by 2 the whole square using binomial expansion. I'll get this. Right. So which is equal to minus 1 by z. I can rewrite this as in terms of n. Generally, I can write, right? Summation n equal to 0 to infinity 1 by z the whole power n. Next, minus 1 by 2, if I take it out, I'll get z by, summation n equal to 0 to infinity z by 2 the whole power n. Understood? Right, last condition is this. What is the last annular region? Mod z is greater than 2. Yes. So mod z greater than 2 means, you all remember, whenever this condition is supplied, radius is 2, center is 0. So we have to cover the function where it is analytic, we have to find which is exterior to this circle. This is the mean. Can you all understand? So 0, 1, 2. So this is the circle of radius 2. So I have to find the expansion of the analytic function exterior to this circle, right? With this information, as usual, f of z, where is our f of z is here, like minus 1 by z minus 1 plus 1 by z minus 2. Now come on, since so mod z by 2 less than 1 means, I think I have to find the condition, like as per the unity, I have to take 2 by mod z should be less than 1. From this I'm getting this, which implies 2 by, what I say is correct, right? 2 by mod z is less than 1, which implies 1 by mod z is also less than 1. So from this condition, 2 by mod z, can you see the condition? 2 by mod z is less than 1, which implies 1 by mod z is also less than 1, right? So here what I have to take it out then? So if I take z out, I'll get the point 1 minus 1 by z, plus here also what I have to take it out? Z out, 1 minus 2 by z, right? Yeah, actually students, we are dealing Taylor series here. Before that, Taylor series over. Here we are expanding the analytic function using whom? Lorentz series, right? So minus 1 by z. So bringing the denominator to the numerator, 1 minus 1 by z the whole inverse, plus 1 by z, bringing the denominator to the numerator. So as per its request, it came because it should contain both positive and negative series, right, terms. So 2 by z the whole inverse. Now minus 1 by z, I took it out. So 1 plus 1 by z plus 1 by z the whole square, etc. I'll get, plus 1 by z, 1 plus 2 by z plus 2 by z the whole square, etc. will get, isn't it? Yeah. So close the bracket. So it is equal to minus 1 by z summation n equal to 0 to infinity 1 by z the whole power n plus 1 by z summation n equal to 0 to infinity 2 by z the whole power n. So here the problem ends. So I think I'll conclude now. Thank you.